Buffers are important in biochemistry. Living organisms depend upon buffer systems. Many reactions must be buffered. Anytime you need to carefully control pH, you use a buffer. A buffer resists a change in pH. It is composed of two species, a weak acid and its salt, such as acetic acid and sodium acetate, or a weak base and its salt, ammonium hydroxide with ammonium acetate. If you have a buffer system with hydrofluoric acid and sodium fluoride, then you add a little bit of hydroxide to that solution. The hydroxide will react with the undissociated acid to produce water and fluoride ions, so the pH remains constant. If you take this same buffer and add some acid to it, that will react with the fluoride ion to produce undissociated acid. Thus, the pH remains the same. So how do you do the calculations? First, let's write the reaction for a general acid, and that's where we use HA. A represents an anion. Then once we write the reaction, we can write the equilibrium expression. Then we're going to rearrange this just a little bit because we want to get this in a form that's easier to use. So once we have that form, we take the negative log of both sides and we get this expression, and notice that minus the log of Ka is the pKa, minus the log of the hydrogen ion is the pH. The anion is a base and the HA is an acid. So we identify the parts. Then we're going to substitute these values into a new equation equivalent to the one above, and then rearrange again. And this is now in the form of what we call the Henderson-Hasselbalch equation, which is a very useful equation for solving buffer problems. So let's have an example. We've got a solution that is 0.12 molar in lactic acid and 0.1 molar in lactate. So the first thing to do is ask, is this a buffer system? If it's a weak acid and the salt of the weak acid, it's a buffer system. Then we need to identify the different parts of the Henderson-Hasselbalch equation. What is the concentration of base? What is the concentration of the acid? And what is the Ka? And once we have the Ka, we can calculate pKa. Now we're going to take those values and substitute into the Henderson-Hasselbalch equation. And then we're going to solve that and find that the pH is 3.77. How can we predict relatively what the acid strength is, the ability to dissociate? There are some criteria to help us understand what we look for to make that prediction. The bond to the acidic proton, the HA bond, must be polar. Weaker HA bonds can be broken more easily, thus making the acid strength stronger. The more stable the anion, the stronger the bond. Now, binary acids follow the periodic properties. A binary acid has an ionizable hydrogen with one other nonmetal, such as HCl. Acid strength increases as the anion is further to the right on the periodic table and further down in the group. Oxyacids have a hydrogen atom attached to an oxygen atom, which is then attached to another electronegative atom. Generally, for acids with similar structure, as the electronegativity of the nonmetal increases, the acidity increases. If the oxyacid has atoms of the same element but increasing numbers of oxygen atoms, acid strength increases with the number of oxygen atoms. Carboxylic acids are organic acids containing the COOH group. These acids are very common in nature. The hydrogen on the carboxylic acid is ionizable or acidic. The second oxygen will stabilize this system because the electron density can spread from one oxygen atom to another. We commonly call this resonance stabilization. Acids and bases have important roles in chemistry, biochemistry, earth science, and so forth. To make real-life predictions, we need to understand acid and base strength. We need to be able to calculate equilibrium concentrations. As you have seen, like math, you have to use all the chemistry you have learned to solve these problems.